In this problem, we'll take a look at the vapor pressure of a liquid. And now, even if you're below the boiling point temperature, a liquid will evaporate to some degree. If you have, for example, a glass of water, leave it on the counter, that water is not boiling, but you come back the next day and some of it will have evaporated. So we have an enclosed system over here, 0.25 liters. We have some butane liquid, and some of this liquid is going to evaporate. And the question is going to be how many grams of vapor how many grams of the liquid is going to evaporate. So we need to find the vapor pressure at this temperature. And to do that, we are given the normal boiling point, and the normal boiling point is when the vapor pressure is equal to the normal atmospheric pressure, which is 1 atmosphere. So we have that. We're going to use the Clausius Clapeyron equation to calculate the vapor pressure, how much the vapor pressure of this liquid, of the butane vapor above the liquid. We have the natural log of P2 over P1 equals negative delta H over R, 1 over T2 minus 1 over T1. Some professors flip this and make that positive, so pay attention on how this formula is presented in your class. I'm going to plug in all these numbers over here. I'm going to call the cold state 1, and then the normal boiling point temperature 2, and the hot one 3. And I'm going to plug in numbers. Delta H is given to us as 22,440 joules per mole. They gave it to us in kilojoules. We have to change it to joules. And the R value, we're going to use the energy R value, the 8.314 joules per mole degree Kelvin. We do this calculation, inverse E raised to that, and we get a vapor pressure of 0.436 atmospheres. So that's the vapor pressure in here, right? 0.436, etc. atmospheres of vapor. Now we're going to use PV equals nRT to calculate how many moles and consequently how many grams of vapor there are. So we're going to plug this into PV equals nRT. The moles is PV over RT. Now here we're going to use the 0.08206 because we have atmospheres, and we get however many moles of CH4 of butane, multiply that by the molar mass, and we get how many grams of vapor are in here. And so that's going to be 0.308 grams of vapor, which means that, subtract that from the original amount, 0.7, and we're going to have 0.4 grams of liquid remaining. So that's the first part. The second part is at the hotter temperature. Now at the hotter temperature, again, if there is enough room, all of this will evaporate. So we're going to go ahead and let's go through this process. We'll do natural log of P3 over P2 equals negative delta H over R, 1 over T3 minus 1 over T2. We're going to plug in, let's see how much vapor is present, that can be present. We don't know what the vapor pressure is over here. This is our P3. We're going to put P2 is this one here, 1 atmosphere. And then negative 22,440 joules per mole, 8.314 joules per mole Kelvin, 1 over 298.15, 1 over 272.75 Kelvin, and we go through this process and we get the inverse natural log. I'm going to hit pause right here. Okay, do this calculation. We get this side is 0.843. This is natural log, which is base E. So E raised to that is going to give us P3. So that's our pressure over here in here, 2.32 atmospheres. Let's plug that into PV equals nRT. So we have the pressure times the volume, which is 0.25, divided by 0.08206, divided by this temperature, 298.15, and we get 0.0237 moles of vapor. But butane, 1 mole of C4H10 is 58 grams, and so that's going to be times 58. So that means that we're going to have 1.38 grams of vapor. But be aware, we only had 0.7 grams to begin with. So basically this would be the maximum amount of vapor that can be present. So 0.7 minus 1.38 will give you a negative number, but basically no grams of liquid remain. All of the liquid will have vaporized.